Hi everyone, my name is Martijn, and today I will be talking about our work quantifying language variation acoustically with few resources. This is joint work with my supervisor Martijn Wieling. Self-supervised models have improved automatic speech recognition substantially in recent years. However, it is relatively unknown if the learned information also transfers to other tasks and other languages. This is important when developing more inclusive speech technology, especially when the resources for training such models are lacking, such as for regional languages and dialects. In our previous work, we found that representations from hidden layers of these models contain useful information for representing pronunciation differences. In this study, we want to find out whether we can use these hidden layers to model fine-grained pronunciation differences between regional varieties in the Netherlands. Our code and models are publicly available on GitHub and Hugging Face. We use Dutch dialect pronunciations from the Goeman Taaldeman van Renen project. Unfortunately, the hour-long recordings were not segmented, and the metadata with the timestamps were not always available. We therefore extract a subset for 106 villages in the Netherlands that contains 10 words per village. On average, this is only 6 seconds of speech per village. Now on to the methods. We compute embeddings from the hidden layers of 3 Wave2Vec2 large models. We use a new Dutch model, an English model that was already provided by the authors of the Wave2Vec2 paper, and a multilingual model that we fine-tuned on Dutch label data. Using these embeddings, we compute word-based pronunciation differences per layer using dynamic time warping, and also compare this to phonetically transcription-based differences that we compute using the Levenshtein distance. We average word-based differences between a pair of villages to obtain a single difference score, and repeat this process for every pair of villages to obtain a distance matrix for each of the layers per model. We cluster these difference matrices into 4 groups. 3 groups correspond to the regional languages that are recognized by the European Charter for Regional or Minority Languages, and these include Frisian, Low Saxon, and Limburgish. The 4th group is related to Standard Dutch. We use 7 different clustering techniques per layer and select the best one by calculating the cophonetic correlation coefficient. The results per layer are then compared to a gold standard clustering using the C-distance score that was presented by Kuhn and colleagues. And this measure allows spatial information to be included in the evaluation. We see that the multilingual model that was fine-tuned on Dutch data with output layer 15 and complete link clustering showed the best performance. All acoustic models outperformed the traditionally used Levenshtein distance. Importantly, the multilingual model outperformed the 2 monolingual models. We know that the multilingual model is pre-trained on a variety of languages, including German, English, and Dutch. And the regional languages in our dataset have clear links to these languages. On this slide, we show the gold standard clustering together with the fine-tuned acoustic models. We see that the multilingual model clearly distinguished the Limburgish pronunciations that are shown in light green better compared to the other models. While the multilingual model does not perfectly distinguish the Low Saxon pronunciations, the other models perform a bit worse in this regard. So to wrap up, the multilingual model that is fine-tuned on Dutch label data can be effectively used to distinguish between regional languages in the Netherlands. And multilingual pre-training and fine-tuning on a language that is similar to the target languages is beneficial over using a monolingual model.